So we're going to get these videos working soon. So my name is Hernandez. I'm a second-year electrical engineering major, and I am working in the robotics lab for the summer as a EUREKA scholar under the mentorship of Guillaume, who's right there. And when I was working, my project consisted of path planning and tracking for autonomous cars. So without further ado, let's get started. Alright, so why is this all relevant? So there's three main ideas that we hope to work towards with this project. And these are safety, energy, and speed. Because if we can program a car to operate it by itself without the human well, the human can help it, but if it can operate by itself, in theory, it could be more efficient than the human, and it could potentially reduce the amounts of traffic accidents and other delays that we as humans cause with our human intuition. And something else that we can do is, because we are using with autonomous cars, there's a chance for reducing the fuel, and this can come where we are using the best path possible, because sometimes we make a wrong turn or we miss an exit, again because of human error. So if the car already plans this and it knows which way it can go, it can minimize the time and the distance that we travel to get to our destination. Another one is speed, because again, going back to the routes, if we take longer to get where we are, it's likely due to something such as traffic that some people are causing because they also either missed an exit or they don't know where they're going, but it's okay because we're all friendly in the driving community. And so since the beginning of time, we have the cars that had no autonomy, but over the years we began developing minor autonomous features, such as we got the cruise control. You've seen those commercials where it says, buy this Nissan, it'll park by itself. And then you also have the current Tesla working on their latest innovations, but we're trying to get step 5, which is full autonomy. So how will we do this? I'm glad you asked. Alright, so first of all, before how we do this, let's see what we want to do. So we're trying to get the car to move from one starting place in orientation to the next one. And we're trying to use this with the simulation. And essentially, I'm trying to get the simulation to run so that I can transfer that information to the real car itself. And for the further longer term goals, the first bullet point, to avoid and exploit wheel slipping, this is if we can get the car to go fast enough and we could turn at a certain angle to make the car skid, we can try to find this boundary where the point where it slips so that we can either maximize our speed without reaching the boundary and slipping, or get to the boundary as soon as possible and use the slipping to our favor. So here we have the simulation that we're working with, and the goal is to get that to the real thing itself. That's our car. So for hard coordinate system, this is something more of a background knowledge that the rest of the presentation can be more concise, more clear. So we're working with this general coordinate system where we're going to have 3 inputs to our order pair. We're going to have the X position, the Y position, and the orientation. So the orientation refers to the angle that the car is facing with respect to the axis. So for instance, the A arrow is the position 3, 3, and it's roughly pi over 6 degrees. Whereas the B arrow is located at 5, 9, and it's negative pi over 2 degrees. And then as you saw in the previous one, the one that was facing down was negative pi over 2 degrees, but the unit circle usually goes from 0 to 2 pi. And why is that? Well, this is because we have a car, and if it's facing nothing, it's going straight, then it's considered to have a 0 radius of the orientation. Whereas if we turn it this way, it's going to be negative pi over 2. Why is it negative pi over 2 and not instead 3 pi over 2 like the traditional unit circle? Well, that's because the car can go left or right. So it would make more sense to make a right turn as opposed to make a left turn for a whole 270 degrees and then get to where you want. And then in this case, it's just facing the pi over 2 radians. So the process, essentially this is, it's a 3-step process that I'm working with. First one is the path planning. Once the path is planned, we gotta get that on the simulation. The simulation tracks it. From the simulation, we get it onto the car itself. So, step one, path plan. So for the path planning, we're trying to use this thing called a Dubin's path. And so a Dubin's uses a turn radius so that it can try to get from one position in orientation to a second position in orientation using the shortest route with the fixed turn radius. And this path can be consisted of a curve and a straight and a curve, or a curve and a curve and a curve. So these are some of the few possibilities, but it's limited to, or it can consist of mostly 3 segments. Like here we have one curve, a straightaway, and another curve. But we only use these as needed. So if like it were to end right here and face right, it would just be a curved straight path. But it uses, in theory, it is with a combination of 3 segments, we can create the path. So the curve, 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 and these are 2 general paths that can be narrowed down to. And so for the basics, for Dubin's, we have this thing called a turn radius. What exactly is the turn radius? Well, let's say you have a car turn with these angles, with the front wheels at this angle. If you go at a constant velocity the whole time, you'll get a circle roughly like that. Whereas if you turn the wheels a little more, you're going to get a smaller circle. This comes into play because if you're trying to get somewhere that's not as far away, but with a large change in the orientation, your car can't just do a U-turn. It's going to have to go around and do a longer trajectory, as opposed to if it's far enough and you can turn sharp enough, you can get to the orientation with just one simple turn. And with starting position and orientation, I'm just referring to where does it start. Here, it's starting at some point. Let's just say 0, 0. It's facing up, pi over 2. Right here, it's shifted x units to the right, and it's facing negative pi over 2. And so once we get the path to work, now comes the simulation. And the way we do this is, the path is essentially a series of points. And the goal is to get the car to track to each point individually. We calculate this by checking where the car is at the current time step, seeing where the next time step, where it should be at the next time step, calculating the error between these two, and then adjusting the steer angle with the proportional controller. And so that would look something like this. So in each case, the car was trying to not do it's not trying to do the whole trajectory at once. It dissects it into each point individually, so that it can follow the path. And so with this path right here, this is an example of something that we could track, but for our sake, we're going to be doing something a little simpler. And so now we got this video. We got the videos to work this time. So for the simulation, the turn radius input was 1. Our velocity was roughly 1.5 meters per second. In the simulation, each square it represents a meter. Our starting coordinate was 0, 0, 0, and our target is 0, 2 pi. So it's going to be translated 2 units up and be facing the completely 180 degrees the opposite direction. So wow. Do it one time, speaker. Wow. Alright, so once we get the car, once the car tracks the path accurate enough, we're ready to transfer that to the real world, the hardware, as we call it. So now we're to the hardware tracking. Okay, so starting positions again were 0, 0, 0, and everything else is the same turn radius. But in real world, because the conditions are different, the speed that we used was 0.70 meters per second. And for the sake of labeling stuff, the x-axis was this way and the y-axis is that way because the car is initially facing this direction, and when it goes in the original direction, that's going to be the x-axis, and this is going to be the y-axis. It's just a slight rotation of the camera, the way it was adjusted, so let's get this going. Let's do it one more time, Is it nice and pretty, but you know, it took a while to get there because initially it would just stop right here, it would turn too quick and go inwards, it would almost crash the desk that's right here somewhere. We essentially got to our goal. So, okay. So now we're going to be comparing the data with the simulation in the real world. So with the simulation, as you can see, or as you guys might have seen, the path desired and the track were very close to each other. This was all done because in the simulation, everything is ideal and we get things the way we want. But within the real world, that's not the case. As you can tell, there was a minor error. This can be due to the camera not tracking the car accurately the whole time, and also the conditions are different. So we expected something to be some error, but the amount that we got was little, so that's good. And so, based on that, that's the actual car on the right. We can see there's factors responsible for this error with the simulation in the real world test. One of them is the dynamics. So we didn't notice it at first, but it turns out the car in the simulation is a little longer than the car in the actual life. So this comes into play because since the car is longer in simulation, when it turns, it can go further out, and we had sort of a small inward turn. So that was one of the factors that come into play here. And another one was that the simulation again has ideal conditions, and all of this is stuff that we still have to take into account to try to get the hardware to be working more accurately. And as for improvements yet to come, we're going to try to fix this scaling issue with the simulation so that when we transfer it over to the car, it can be more accurate. And even further than that, we're going to try to make the car run by itself and not depend on the simulation, because the way it works right now, the simulation transfers the data to the car, but if we were able to get the car to operate by itself, so they kind of implement the code of the simulation onto the car itself, we can get the car to update by itself automatically. That's going to be more accurate as opposed to trying to mimic what happened in the simulation. And in addition to that, we're going to put LEDs in the car so that it can help with the orientation, because sometimes with the camera, see this right here, it's a circle. So this identifies the car, and then the little line finds the orientation. This line tends to squiggle from time to time, so that can kind of mess with the orientation. And if we get the LEDs to make the line be more precise, that's going to be it's going to be more accurate in the future. And so, conclusion: we did some path planning, some path tracking, and we analyzed this data. The path planning means the difference path. Path tracking, we use the controller to adjust between the area that we want to be and where we are. And to analyze the data, we implemented the stuff we learned from the previous trials so that we can improve the future tests. Thank you. Simone, for making this all possible. My success is possible, and most of all, my mentor Guillaume, because I know this is kind of an advanced subject and it takes a lot of patience to be a mentor, so thank you.